Hello, everybody. Welcome back to class. Our final full week. Can you believe it? Well, you know the drill. Let me know who's here. Say hello. Looks like nobody's here. That's fine. Jax is here. Reagan, hello. Navik, good morning. James says, good morning, Professor Amelia. Don't call me Professor Amelia. Hello, Ellie. Hello, Lauren. Hello, Jared. Hope everybody had a good weekend. Good morning, Jonathan. Today I've got green rubose Maribel tea. Interesting. How was the 9 o'clock class? Ask Navik. He was there. Hello, Turner. Welcome back to class. To be honest, 9 o'clock class today, they were a little quiet. Tough. It was tough material. Hope everybody got started with the WebAssign. It's due tonight. It's quite a bit of it, but it's good practice. All right, well, it's 10 o'clock, so let's get started. Good morning, Molly. Yeah, it was not easy, said Navik. All right, so if you have your coffee or water or green rooibos Mirabelle tea, feel free to join me in this simultaneous sip. I hope you all joined because that was the first simultaneous sip of a full week. For the rest of the semester. All right, so it seems like a few of you have joined. So what we'll do today is we'll start off with a warm-up. Don't want to go out too fast, you know what I'm saying? So we'll start up with a warm-up, crank out 3 integrals, and then we'll move on to a kind of an application of integration. And depending on how far we go, maybe we'll get into section 4.5. So before we get started, remember we have a test on Friday. It'll be set up just like the last one. I'm hoping to get done with the material tomorrow so we can review on Thursday. Basically, just know how to do integrals and you should be fine. Okay, but take a look on Canvas because I posted a bunch of review material. All right, let me write out some integrals. I'll write out all 3 so you could crank them out all at once if you'd like. All right, so the first one is evaluate the integral from 0 to 3 of 2x to the third minus 6x dx. The next one is the integral from 0 to 12 of x minus 12 sine of x dx. And the last one, which is probably the hardest, okay, the last one is evaluate the integral from 1 to 9 of 2t squared plus t squared square root of t minus 1 all over t squared. Okay, so I'll give you a few minutes to try to work these out. Yeah, maybe just put like a confetti or a celebration bit emoji in the chat if you feel like you solved one of the questions, and then if you feel like you've solved the third question, maybe like a fireworks emoji. Okay, I won't call on you unless you want to share your answer. I just want to kind of get a vibe for, you know, how long I should give you guys to work on these questions. All right, so for these first two, confetti emojis or, you know, smiley face or something. This one, something over the top, okay? Because this one's harder. And if you need any help, just put it in the chat. I'm just standing here like literally staring at a wall. So I'm happy to help. Just as a reminder, how do we integrate these? Right, this is just a polynomial, so you could increase the power by 1 and divide by the new power. That'll give us the antiderivative, and then we have to figure out what to do with these bounds. Might have to look at your table of integrals to figure out how to integrate sine, but you guys are smart. You can figure that out. All right, has anybody had luck with any of these? Maybe is the chat broken? All right, here we go. We got a little feedback. First, firework. Jared thinks he's got the last one. That's nice. All right, I'll give you guys maybe 30 more seconds, and then. Okay, good. Yeah, I'm just never sure if you guys are working or if the chat is broken or what. This is truly a tough situation. But yeah, let's start cranking through these. Again, these integrals, they get easy with practice, but you do need to practice. Okay, to evaluate the integral of 2x to the third minus 6x, we're just going to increase each of the powers by 1 and divide by the new power. So it's 2x to the fourth over 4 minus 6x squared over 2. Now, you may be thinking, why don't we have plus c? Well, the reason why we don't need the plus c is because we're going to be evaluating at these endpoints, and we'd have like a c minus a c when we did it out. So we don't have to write plus c for a definite integral. evaluating at the endpoints. So when we evaluate at x equals 3, and when I write out this answer, I want to see in the chat if anybody got this or if they didn't get it. When we evaluate at x equals 3, we get 81 halves minus 27. And then when we evaluate at 0, we get 0. So 81 halves minus 27 is 27 halves. All right, so let me know if you got that. All right, for the next one, again, we're going to increase the power by 1. A nice few of you got it. That's good. That's good. Increase the power by 1, divide by the new power. Now here, we don't have a polynomial. We don't have x raised to a power. We have minus 12 sine of x. The antiderivative of minus 12 sine of x is positive 12 cosine of x. Right, now we can evaluate at the endpoints. And when we do that, we get 144 over 2 plus 12 cosine of 12 minus 0 plus 12 cosine of 0. This is 72 minus 12, so 60 plus 12 cosine of 12. All right, and so like the last one, let me know if you had any luck with this one. Here it shows the importance. You know, sometimes you get in the habit where you only evaluate at the top endpoint, and it's really not going to mess you up too much. Here you see you have to evaluate at the lower endpoint as well because we subtracted off 12. All right, so how about for this third one? How do we start the third one? Right, we don't know how to evaluate the integral of a fraction. So how can we get started here? All right, well, I'm going to assume there's a delay. What we could do is break it up into 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared. Yeah, what you said, Jax. Treat each part of the numerator as a separate fraction because it's all in the same denominator. And Bella, you're right as well. Split it up into 3 fractions. Good, good. Yeah, and so now this is easier, right? 2t squared over t squared is just 2. plus the square root of t minus 1 over t squared. Okay. How do we deal with the square root of t? How do we deal with 1 over t squared? The way we deal with the square root of t is we write it as t to the 1/2. And the way we deal with t squared is we write it as t to the -2. Right? And now this should be really straightforward to integrate. So it's 2t plus 2/3 t to the 3/2 plus t to the -1, evaluated at our endpoints, which are 1 and 9. Right, when you divide by 3/2, it's the same thing as multiplying by 2/3. And here we would have had a negative, and then we would have divided by -1. So 2 negatives turn into a positive. All right, so now let's just plug in the endpoints. Turns into this. And if you work this out, right, I mean, this is a calculus class. It's not an arithmetic class. So the fact that you got to here shows that you understand calculus. You know, going from here to here means that you either know how to type numbers into a calculator or you're good at arithmetic. Okay. Yeah. Any questions on those? Feel free to ask them in the chat, but if not, we're going to move on. So we'll state a theorem. It's called the Net Change Theorem. And what's it say? It says, if an object moves along a straight line, with position function S of t, then the integral, so okay, well then v of t equals s prime of t. That's not the theorem. And the net change of position or displacement is given by the integral from t1 to t2 of v of t dt, which happens to equal s of t1, s of t2 minus s of t1. Right, so if you want to figure out how much our position changes over a given interval, you take the integral of the velocity function. Right, so if you take the integral of the velocity function, it tells you, how much your position has changed. It doesn't tell you your total distance traveled. It tells us how much the position has changed. For instance, if you were to be on campus and then you drove downtown and then drove back to campus, your displacement would be 0, but your distance traveled would not be 0. Okay, so this tells us our displacement. So let's take a look at an example, or I guess before we get to the example, the total distance traveled is the integral from t1 to t2 of the absolute value function v of t. Okay, so if you take the integral of the absolute value of velocity, that's going to tell us how the total distance we would travel. Okay, let's look at an example. A particle moves along a line so that its velocity, I'm just going to write out the important parts, v of t is equal to t squared minus t minus 6. Find the displacement on the interval 1 is less than or equal to t, less than or equal to 4. And then B, find the total distance traveled during this period. All right, so for A, we want to find the integral of the velocity function. For B, we want to find the integral of the absolute value of the velocity function. So A is pretty straightforward. Does somebody in the chat want to explain how they might go about solving part B? All right, well, when we get to B, we'll talk about it. Okay, so A just wants us to find the displacement. The displacement is just the integral of the velocity. So increase the powers by 1, divide by the new power. Evaluate at the endpoints. So when we do that, we get 64 thirds minus 8 minus 24 minus 1/3 minus 1/2 minus 6, which is negative 9/2. Okay, so our net change in position, we went backwards by 9/2 units. All right, so this next part is the harder part. So how do we find when our velocity is positive and how do we find when our velocity is negative? Right, because that's really how we're going to deal with this. So what we want to do is let's find when our velocity is equal to 0, right? This is the same exact question as asking like when is a function increasing or decreasing, which we'd spent a month doing basically. We set our function equal to 0 and then take test values at each part of the number line. So v of t set it equal to 0. So that's t squared minus t minus 6 equals 0. This factors into t minus 3, t plus 2. So we'll take our interval, and we'll break it up at each of these points. Now notice -2 is not in our interval, so we don't care about it. Right, and now we'll just take a test value. V of 2 is a negative times a positive is a negative. V of 3.5 is a positive times a positive is positive. So we'll take our integral, we haven't written out yet. And we'll break it up. We'll first integrate over this region. We'll integrate over the first region of the negative velocity, right? Why is it the negative velocity? Well, our velocity is negative on that interval. So if we multiply it by -1, it becomes positive. That's how the absolute value function works. And on this part of the interval, it was already positive. So we don't have to do anything to it. All right, so This is equal to integral from 1 to 3. Negative v of t is negative t squared plus t plus 6 plus the integral from 3 to 4 of v of t. Is this process true for any absolute value integral? Yeah, that's exactly how we'll do it for any of these types of absolute value integrals. Is you would find on which intervals is our function positive, and then just deal with that one normally. And then on any part where our function would be negative, we multiply it by -1. So you could imagine we'd have to break it up at a lot of spots if the function changed sign a lot. But yeah, that's how you do it. You'd find each time where our function, right? Because really what's happening here is the absolute value function is a piecewise function. So we're breaking it up at each of its pieces. Okay, so let's evaluate this. And when we evaluate this, so you could try this on your own, but it works out to be 61/6. All right, so go through and do this algebra just to make sure that you get this answer. But so our total, what this is saying, our total distance traveled is just about 10 units, but our net, our change in position was we went backwards by -9/2 units. Yeah, so I would go through and just evaluate the function at these endpoints just to confirm that you like this number, but we're not going to do that today because I'd rather move on to the next topic. If you want to see another example of an integral of absolute value function, I posted one to YouTube a few days ago. Okay, so let's move on to section 4.5. Which is the substitution rule. What this is saying is, well, just note our antiderivative rules don't tell us how to integrate all functions. They're missing most functions. So our antiderivative rules don't tell us how to integrate functions like the integral of 2x times the square root of 1 plus x squared. Will this be on the exam, 4.5? Yes. This will be the last part of the exam. Well, this will be the last topic on the exam. I don't know where the question will literally be in the exam. Okay, so suppose we have a function like this, right? We have like, instead of just having an x in the square root, we have a 1 plus x squared in our square root, and we have a product. How do we deal with this type of integral? Well, I'll tell you how we're going to do it. So to find this integral, we're going to switch from the variable x to the variable u. Okay, and we're not literally just going to switch all the x's to u's because that would tell us nothing. We're going to kind of do it in a clever way. So we'll say let, in this example, and again, this is just, a lot of this is just going to be, kind of seeing patterns with practice. Getting good at it by doing a lot of examples. So in this example, we'll let u be the inside of the square root. So we'll let u equal 1 plus x squared. So the derivative of u, this differential, is 2x dx. So our integral well, we could rewrite this just for clarity. This is the square root of u, and this is du. And we know how to evaluate the integral of the square root of u. That's 2/3 u to the 3/2 plus c. But that's not our answer. Right? If I said, oh, evaluate the integral of 2x times the square root of 1 plus x squared, and you said, oh, it's 2/3 u to the 3/2 plus c. I'd be like, what the heck is u? Right? So this is not our answer. We have to get back to the variable we started with. So you would take your u's and replace them with 1 plus x squared. So to evaluate this integral, which looks a little bit complicated, you just got to notice, well, this inside function, 1 plus x squared, its derivative is on the outside. Maybe we could try to use that as a U-substitution. So what I'm going to do now is I'll write out in general how we do U-substitution, and then we could work on an example. Okay, So this is called the substitution rule. Okay, so if u is equal to some function, g of x here is 1 plus x squared, is a differentiable function whose range is some interval I. So if u is equal to g of x, it's a continuous function, and f of x is continuous on the domain on the range of u. All right, so basically what this is saying is we're allowed to take the composition of f and u. Then the integral of f g of x times g prime of x. So the way we reverse the chain rule, right? This is the derivative of f of g of x, this inside part here. The way we reverse the chain rule is we will let u equal g of x. du would be g prime of x. Okay. So if we have a function and its derivative on the outside, then we could take that and replace it with the variable u, and then integrate with respect to this new variable. Again, it's going to become clear with just some practice. So let's look at an example, and this is all we're going to do tomorrow also. Okay, so we'll have a full class of practice with this. But I do recommend you should probably try to crank out at least 10,000 of these before the test if you want to be an expert like I am. No, but you should practice. You should do a lot of practice for these because literally this is the only way you get good at them. All right. So find the integral of x to the third cosine of x to the fourth plus 2 dx. Okay, so does somebody want to make a guess for what they could use for u here? 10,000 should take you 10 hours. Yeah, probably more. Does anybody have a guess for what we could use for u? Yeah, we could use u as x to the fourth plus 2. But then we got to somehow make it so the derivative of u is on the outside. It's close, right? The derivative of x to the fourth plus 2 is 4x to the third. So we could multiply this by 4, but we'd also have to divide by 4 in order to not change the value. But yeah, that's exactly right. u is equal to x to the fourth plus 2. And see what we get. So let's just work this out. Again, you guys have the power to just mute me if you want to keep working on your own. Okay, so we'll let u be the inside function here, x to the fourth plus 2. Which means du is equal to 4x to the third dx. One way to think of this is here we have an x to the third dx. So we could solve for x to the third dx if that's what you'd prefer. So x to the third dx is equal to du over 4. Okay, so our integral, which is x to the third cosine of x to the fourth plus 2 dx, is equal to, well, we can replace cosine of x to the fourth plus 2 with cosine of u. And we'll replace x to the third dx with du over 4. So we'll put the 1/4 on the outside. Du. Okay, and now the question is, what is the integral? All right, this is a much easier question now. What is the integral of cosine of u? Yeah, it's sine of u. So this is 1/4 sine of u plus c. And then the last thing we should do is make sure we finish our question in the variable we started with. Right? Because this is just total gibberish if we don't know what u is. So we should replace it with what we started with. Amazing, isn't it? All right, let's do one last example. All right, so does somebody want to say what they're going to use for u in this example? Yes, excellent, Turner. Thank you for sharing your answer, because that is correct. We could use u as 2x plus 1. So du would be 2 dx. And again, we could solve for dx, right? There's nothing else. There's not a 2 here. So let's solve for dx. We get dx is du over 2. Okay, so our integral we could write as 1/2 the integral of the square root of u, du. Which is 1/2 u to the 3/2 over 3/2 plus c, which is 1/3 u to the 3/2 plus c. And the way we finish it off is we replace all the u's There could be a lot of them. We replace them all with 2x plus 1. All right. So, yeah, that seems like a good place to stop for today. I have a YouTube video on U-Substitution coming out at like 12 or 12:15. Those of you on the notification squad, which I would imagine is all of you, you'll get a notification when it goes live. But those of you who aren't on the notification squad, you know, there's another video coming out at, I don't know, 12:30 or 12:15. It's challenging, but I recommend looking at what the question is and don't watch my solution until after you give it a try. It's about as hard as you would see a U-substitution question in this class. So I would look at the question, try it on your own before you look for the spoilers. But it's good practice. Okay. Yeah, so tomorrow we'll just keep doing more practice with U-substitution. We'll talk about how to do U-substitution with definite integrals, which is good stuff. Yeah, remember to hit the like button before you get out of here. I have office hours this afternoon, I believe. So if you need some help with the WebAssign, feel free to stop by on Zoom. That's all I got. So I'll stay around for a little to answer any questions, but I'm going to sign out in a second. Does @Molly Lynch stream her class too? No, she does private Zoom. See you, Turner. Is anyone holding at home? I think we're all staying at home. When is the final? The final is May 4th at 9:00 a.m. All right. Bye-bye.